Hi again, everyone. I guess some of you heard us talking in the beginning. I am Antara Dasgupta. I am now at the RWTH Aachen University, and I'm here today presenting our project, DestinE, Digital Twins for Global Flood Risk Reduction, with my colleague, Patrick Matgen, from the Luxembourg Institute of Science and Technology. Patrick, maybe you want to introduce yourself briefly?
Thanks, Antara, and hello, everyone. So it's a real pleasure to present to this community that I like very much. So yes, as said by Antara, I'm Patrick Matgen. I'm at the Luxembourg Institute of Science and Technology, and looking forward to this presentation.
Super. Right, so without further delay, let's dive right in. So you must have heard a lot of buzz in the recent last 2 years, actually, to be precise, about the digital twins of our planet. And a lot of you might be wondering why now? So what is the context of this? And one of the things, of course, that enabled this were the concurrent rise of enabling technologies such as AI, cloud computing, IoT, HPC, what have you, and simultaneously this boom in new space and public satellites and open data programs enabling us access to these really large variety of Earth observations of our physical world. So as these two things evolved together, it seemed like it was the time that we could start developing methods to combine these data sources, given the large computing capacity that we now had. Aligned with this, the European Commission launched the Destination Earth program, and the ESA, the European Space Agency, launched the Digital Twin Earth program, which will over the next decade plan to fund different components of the development in this direction, and we will see briefly how. So the Destination Earth program, or the Digital Twin Earth program, aims to provide infrastructure as a service, which should be built and operated by the industry, but serve the needs of the community, as well as the user community, as well as the scientific community, aiming to provide analysis of Earth systems, specifically looking at extremes and climate change impacts at the beginning, and slowly moving towards anticipating different varieties, different types of environmental changes, and specifically how to adapt policies to combat some of these climate-related changes. And the backdrop to all of this, specifically to our project, is of course this rather noticeable increase in global flood risk, which is here we see on the screen a map of the UK, where it's this is from Fathom, where they show that between 2020 to 2050, a very large number of properties in the UK will increase their flood risk by more than 50%. More than 50% of the properties will increase their flood risk by 1% every year. So this brings me to the state of the art. What do we have right now to combat the flood risk that our populations face? And one of the products that was also mentioned a lot today, of course, one of the landmark products in this direction was GLOFAS under the Copernicus Emergency Management System, which provides stream flow forecasts on a short-term and medium-term basis, produced by ECMWF. And here they provide estimated flood extent at 1 kilometer resolution daily, with a lead time of up to 30 days. So this is the maximum lead time that you could get for these flood extents. And they also provide rapid risk assessment maps based on a comparison of their river flow forecast to a pre-computed catalog of design flood events. So in this case, they model inundations for different return periods, such as from 10 to 500 years. And in the end of 2023, GLOFAS will transition to its 4.0 version, where the static map catalog will be updated to 100-meter resolution and still provide a lead time of 30 days. On the other hand, there is the new global flood monitoring system, again by the Copernicus Emergency Management Service, which provides immediately after the acquisition of Sentinel-1, during a flood event with less than 8-hour latency, a flood map based on 3 different algorithms from TU Vienna, the Luxembourg Institute of Science and Technology, and DLR, the German Space Agency. The three algorithms are combined, as you can see in the bottom figure here, using a majority vote. So this provides the ensemble majority. And at the bottom, you can see that the probabilities produced by all of these algorithms, these are probabilistic algorithms, are combined in this likelihood map that is provided at the end. The limitation of the global flood monitoring product is, of course, that densely vegetated and urban areas are excluded. If some of us are from the radar community, we already know that these areas are challenging still for synthetic aperture radar to detect flooding in. So looking at the limitations of GLOFAST individually and GFMS individually, we can see some ways in which they could be complementary. GLOFAST provides static map catalogs or uses static map catalogs to predict this risk information or rapid impact information. And this is approximated using these return periods, and so not really using the actual flow value. The other thing is that GLOFAST is also rather coarse when looking at the scale of, let's say, flooding in Europe. And the resolution of these forecasts is rarely enough for building level damage assessment. For the global flood monitoring system, the dependency on the Sentinel-1 overpass is a bit of a problem. So earlier, the revisit time used to be 6 days. Now with the failure of Sentinel-1B at the end of 2021, it has been 12-ish days or more in some areas, and this is obviously a problem when trying to observe fast-moving floods. Of course, as already mentioned, we are unable to still detect urban and forest flooding. This is removed from the global flood monitoring system via an exclusion layer. And as an observation platform, it does not have any forecasting capabilities. Of course, this was also not foreseen for the monitoring system, but remains as a limitation. This brings me to the future possibilities with the digital twins. What can we do here? Now, for a long time, we've seen purely in the research context, of course, hydraulic data simulation. So using satellite flood observations, improving flood inundation forecasts by really quite a bit. Here we see on the screen a before and after photo of a simulation, if you will. And we can see that the false alarms are completely removed after simulating just one image. Of course, this is quite the ideal image, not picked here, but we get the idea. So it can be really quite beneficial. And now I will give over to my colleague, Patrick, to talk a bit more about data simulation in this field as one of the pioneers of this particular topic. Patrick, please.
That's why we call this slide the data assimilation dream. So this goes back to 2010 when we started working on that topic. So the idea at that time was, as said by Antara, to combine model predictions with regular observations of flood extent or water depth. And in a first feasibility study, we had shown at that time that when you control the uncertainties of your observations and your predictions, the combination of these two data sets can have an extremely positive impact on flood forecasts. So for many hours and in subcatchments for several days, you can see a positive effect of assimilating satellite-derived water depths into the hydraulic model. But we were not the first to work on that topic. So actually the first scientific paper that I'm aware of that worked on that topic of improving discharge estimates using satellite-based water depth observation was from Andreadis, published in Geophysical Research Letters in 2007. And there have been over the last 13 years many follow-up studies that continue developing these assimilation frameworks, and they got closer to more realistic scenarios where the uncertainties of the predictions of the models and the observations derived from the satellite are poorly understood, and how the assimilation filter can cope with these issues. But now, 13 years later, the question is, why is this not used currently in an operational context? Because as far as we know, no Sentinel-1 data derived flood extent data is currently assimilated into a flood prediction models in an operational context. The only application that comes close to an operational context is that with the recently launched SWOT missions, the assimilation filters or assimilation frameworks developed by Andreadis and his colleagues, they are now used to estimate discharge from the SWOT mission, but there's not yet the attempt to improve discharge forecasting as we have it planned more than 10 years ago. And one reason for this, or could be also seen as an excuse why that this has not been possible, is that simply we lack the data to do that. So in this feasibility study from 2010, we assumed that we would get satellite observations of water bodies every 48 hours. And at the time of Envisat and a few other SAR satellites, that was still far from reality. But now in the last years, and that's why maybe Antara, you can go to the next slide. So with the launch of Sentinel-1, this excuse is no longer valid, because at least up to earlier last year, when Sentinel-1B unfortunately failed, we had over Europe observations every 3 days. So we got very close to this scenario that we had envisioned in 2010. And when you keep in mind all the other SAR satellites that are currently available, and you would all combine them into such an assimilation framework, you can have now an observation of flood extent every day. So I think that the time is there to now get much closer to these operational applications, and that's what we are trying to do in this project. So maybe Antara, you can go ahead.
Thanks a lot, Patrick. So let's go now to the vision that we have with this project. So Patrick outlined really nicely how we got here, really, from the research phase. And now the vision for the future is that with all of the methods developed, the data available, the computing capacity available, really, what are we waiting for? So in this context, we propose here to use the GLOFAST river flow forecasts, which provide global coverage at a daily time scale with a 30-day lead time, really quite unparalleled. And now they will also pre-compute these flood hazard maps at 100-meter daily. Yes, the return periods are fixed, but they are now going to be globally available. And this can be combined within a data simulation framework with the global flood monitoring system, which provides then Sentinel-1 based flood maps at 20 meters at 6 days resolution. These do not have urban areas and vegetations included. GLOFAST, the modeled maps from GLOFAST do. The merging will enable us, obviously, to also compute flood extents in urban and vegetated areas. We would be able to do it at 100 meters, again with a 30-day lead time, and we would be able to produce maps daily. Merging the models with the satellites. So in this data simulation framework, we will be able to improve the global scale flood forecasts, specifically flood inundation forecasts. They will be provided at a daily scale at a relatively high resolution, and an urban and localized context will be included. The algorithm development in general offers quite a bit of flexibility. The data simulation algorithm in principle requires a dynamic model that stitches the time steps between dynamic processes, and we need observations. In this context, the algorithm is model agnostic, that any local model could be used. It's also resolution agnostic, which means that, as Patrick already mentioned, data from any SAR satellite, or indeed any satellite from which we can get a obstruction-free flood map, could be incorporated. It's also regionally transferable. The assimilation algorithm itself does not require calibration or grounding in ground truth data. Of course, the model needs to be localized and requires calibration, as we all know. And finally, the simulation of different types of observational data is also possible. So we try to develop a flexible framework that would eventually also allow incorporating in situ or citizen science measurements, localized weather forecasts, satellite observations of other key hydrological variables, so on and so forth. This should all be possible in the next steps. This brings me to the end of our presentation and kind of to the point. So with this entire context, what we want really is to use this community to understand a bit better what we should be doing